Hello, in this video we're going to cover the materials of Lab 5, which is a continuous of numerical techniques, differentiation, integration, and solving ODEs in particular. Here's an overview of what we're going to discuss throughout this video. First we'll talk about differentiation, then integration, and we're going to discuss both and learn how to implement them numerically or analytically in MATLAB. And next we're going to move on to solving ODEs, either numerically or using symbolic math. And then we'll talk about how to plot or evaluate symbolic expressions in MATLAB using EasyPlot or the function subs. Finally, we'll talk about an introduction to Simulink. In particular, we're going to focus on solving ordinary differential equations with the help of Simulink. Basically, differentiation is a measure of the change in a function with respect to its independent variable. For example, we can say that the derivative of y of x is a measure of the change in y as x changes. There are two methods for calculating the derivative of a function. First method is the analytical differentiation, which is using the formulas. The second method is the numerical differentiation, which we're mainly going to focus on when we discuss differentiation. Analytical differentiation is the calculation of the derivative analytically, basically by applying the derivative formula. Some of the rules for the derivatives of the most common basic functions include, for example, if you have a constant, the derivative of it is 0. If y of x is simply equal to x, then the derivative of that is 1. If y of x is equal to x raised to the power n, then the derivative of y with respect to x is n times x raised to the power n minus 1, and so on. For example, if we have y of x is equal to 2 times x squared plus 4x plus 5, then taking the derivative of y with respect to x results in the expression or the function 4 times x plus 4. We're simply just applying the formulas that we know or that are provided in the table to the expression that is given. This is called analytical differentiation. To find the analytical differentiation of a function in MATLAB, we have to depend on the symbolic math toolbox along with the function diff, which is short for difference or differentiation. For example, if we have this function, the same function we did earlier, and we're interested in finding its derivative with respect to the variable x, then the first thing we need to do in MATLAB is to create a symbolic variable named x, since that is our independent variable. Then we are going to define the function y as a function of x in MATLAB. So we're going to say y is equal to 2 times x squared plus 4x plus 5. Remember, what you see on the left side is the mathematical expression, and what you see on the right hand side is the translation of that in MATLAB. Then to calculate the analytical derivative of a function, we can simply call the function diff by providing it with two inputs. The first input is the function itself, and the second input is the denominator dx. So for example, if you want to derive y with respect to x, then we need to say diff y comma x. So that means derive y with respect to x. And the result, as you can see, is 4x plus 1, which is exactly equal to what we obtained manually in the previous slide. Now moving on to numerical differentiation. When you're given a set of data points such that you don't know the relationship, the exact relationship between x and y, or the independent variable and the dependent variable, but instead you're only given a set of data points x and y, then you can approximate the derivative numerically by applying numerical techniques. And for the derivative, it is simply equal to delta y, or the difference in y, divided by the difference in the x value for that point. And you can do this in 3 different methods. Since you're told to find the difference in y, you can either use the current point and the point that follows it. We're going to see more examples later, but you'll do that for the numerator and the denominator as well. So assuming y of I is the current point at which you want to find the derivative, and y I plus 1 is the point that follows it. In the denominator, you're going to have xi plus 1, meaning the forward point, or the point that follows the current point, minus x of I, which is the point at which we want to find the derivative. Then that is called the forward difference. The second method is to use the backward difference, in which you take the current point and the point that precedes it. The last method is the central difference, in which you take the point that follows and subtract it from the point that precedes the current point at which you want to find the derivative. Now we're going to do an example just to compare the three different methods. We're given a set of data points, x and y of x. X is ranging from 0 until 3 with an incrementing value of 0.5. And then y of x is given as a set of values, so 0, 0.479, 4, and so on. But we already are told that the function is sine of x, only for us to be able to calculate the exact derivative for the sake of the comparison only. So let's check the value of the exact derivative. If you just simply calculate the cosine of x, which is the derivative of the sine of x, for the given values of x, this is what you're going to obtain. Now what we're going to do is a comparison between the three different methods that we've seen in the previous slide. So with the forward difference method, you'll have to take the point that follows, subtract it from the point that precedes, and then do that in the denominator as well. So you'll take 0.4794, subtract it from 0. This is the numerator. For the denominator, it will be 0.5 minus 0. If you do that for the entire column, or all the points that you're given, you're going to end up with these results. And notice that for the forward difference derivative, the last entry doesn't exist because it doesn't have any point that follows it for us to be able to apply that formula. So the disadvantage, or the cons, for the forward difference is that the last point does not exist. And if you notice, or if you compare the forward difference derivative with the exact derivative that is provided, you'll see that the error margin is kind of big because, for example, when x is equal to 1, the error is larger than 0.2, which is big. We can try to make it less than that. Let's examine now the backward difference. So another disadvantage of the forward is that the error is big. Now with the backward difference, we're going to also apply the formula for the backward difference derivative, such that we take the point and compare it with the point that precedes it. Notice that for the backward difference derivative, the first point doesn't exist, since we don't have any point above x is equal to 0 for the given set of data points. Okay, so we can say that the disadvantage of the backward difference derivative is that the first entry is missing. And another thing, if you compare the forward with the backward difference derivative, you will observe that the values are the same, exactly the same, except they're kind of shifted, if you may say, up or down, depending on whether you're talking about the forward or the backward difference derivatives. So since the values are the same, it means the error margin, or the error, is still big. So now let's examine the central derivative, the central difference derivative. Notice that with the central difference, you take the point that follows and the point that precedes. That means there is no first or last entry. So that's one disadvantage. But if you compare the exact derivative with the central derivative, you will notice that they're closer to each other compared with the backward or the forward. That means with the central difference derivative, you get less or a smaller error. So that's one advantage of the central difference derivative. So what we can do or conclude from this slide is that we can create a combination of the forward, the backward, and the central difference derivative so that we take the advantage of all of them. So since the central derivative is closer to the exact value, we're going to focus mainly on it, except instead of the first point, we're going to replace what we have in the central with that of the forward. And then for the last entry, we can use that of the backward difference derivative. This way we'll have a complete data or a complete column for the derivative, and it will be close to the exact value. In MATLAB, you can calculate the numerical differentiation again with the function diff, but observe that if you use the function diff on a symbolic expression, then what you're going to get is the analytical derivative. But if you use the function diff on a numerical array, what you're going to get as the output is the difference between every two adjacent points. That means you can benefit from that to calculate the forward and the backward difference derivatives as such. So this is from the table in the previous slide for the backward and the forward difference derivatives. We can use the diff function as such to calculate the forward difference derivative. I saved the result in a variable named dy dxf, short for the forward difference derivative. And notice that the result, or what I'm storing in dy dxf, is an array whose first set of elements is the difference in y divided by the difference in x. So it's delta y divided by delta x, but it's important that I put the dot since it's an array operation. And then comma, because I want to add one extra input or entry at the end of that array. And that entry is the nan built-in variable. Nan is not a number, or it's undefined. So in mathematics, we say undefined, or it's not there. The reason why we want to add this nan here explicitly is in case we want to plot the derivative with respect to x, and maybe compare it with the function itself, the original function y, and the dy dx forward. So if you remember, when we used the function plot, it is important that the x-axis length matches the y-axis length. So adding a nan at the end makes the array complete, so that it will have a size equivalent to the size of the array x in case we want to plot the derivative as a function of x along with the original function as a function of x as well. What I added at the end is just the apostrophe because I want to take the transpose of the array, so I'll just convert it into a column matrix instead, or a column array. Similarly, we can compute the backward difference derivative by putting first a nan, and then at the end we have the delta y over delta x by calling the function diff on y and x as well. And then at the end, I close the bracket and then use the transpose operator to convert the array, the row array, into a column vector. But we already made comparison between the three different methods, the forward, the backward, and the central difference derivatives, and we observed that each has disadvantages and advantages, especially or more explicitly the central difference derivatives. The central difference derivative had values or results closer to the original or the exact derivative, but it lacked the first and the last elements or entries in it. So what we're going to do is we're going to learn a function in MATLAB that benefits from this data or this comparison, such that it uses forward difference for the first point, backward difference for the last point, and central difference for the points in the middle. So the function name is gradient, and you can use it to calculate the numerical differentiation such that the size of the area you get is equal exactly to the size of the independent variable x. This way you don't have to worry about adding an and at the end or at the beginning, and you'll get a result that is closer to the exact result. So let's see an example. Here we have x is equal to 0 increment by 0.5 until it reaches 3. This is similar to the example we saw from the table earlier. And then y is equal to sine of x. Here, even though I'm using the function as it is, the sine of x, but at the end of this line, or after hitting enter, y is no longer sine of x. It's actually an array, a numerical array. So I'm dealing with the code so far as a set of data points rather than an expression or a mathematical expression. So it is starting at line 3, it's purely just numerical data or a set of data points x and y. So if I call the function gradient in MATLAB, I'm going to obtain the numerical differentiation of y, which is a combination of the central, backward, and forward difference derivatives. And it is used as such. So dy dx is just a variable name that I chose. And the function name is gradient. And you provide it with the expression itself, y. And then the second input you want to give it is the variable you want to derive y with respect to. So gradient y of x simply means derive y with respect to x. So observe that the difference, or actually the order of the input, matters here in MATLAB. And if you ever forget, you can always use the help command in MATLAB just to figure out how to use a function or a method in MATLAB and what inputs it requires, along with the order, the correct order for the inputs. So the result after you hit enter is as such. If you compare it with the table in the previous slide, it will be exactly the same as the central, except for the first point you have the forward difference derivative, and for the last point you'll have the backward difference derivative. Now we're going to move on to the topic of integration. Integration is the inverse operation of differentiation, and it is often thought of as calculating the area under a curve. It can be definite or indefinite. With definite integral, you are given a limit that you want to calculate the integral on, and the result of the definite integral is usually just a scalar, while the indefinite integral is a function or an expression of the independent variable. There are two types or methods of calculating the definite integration of a function. First method is the analytical integration. Second method is the numerical integration, which is an approximation of the definite integration. You can find the analytical integration in MATLAB with the function int. The function int provides a way to calculate the definite and the indefinite integrals as follows. So if you want to find the indefinite integral, you just need to provide f, which is the function itself, as an input to the function int. To calculate the definite integral, you need to have the limits for your integral, for example, a and b. Then you need to use the function int such that you provide it with the function you want to find the integral of, and then the limits of the integral a and b. Since the function int calculates the analytical integral, that means the input of it must be symbolic. So f here, for example, is a function of the symbol x. So if you want to find the integral of the sine of x, then you need to create a symbolic variable and name it x, and then define f such that it is equal to sine of x. Then you'll be able to use the function int with the input f to find the indefinite integral of the sine of x. When you want to use the int function to calculate definite integrals, the limits you must provide can be either numeric or symbolic. For example, we're going to do now an analytical integration with the help of the function int on the function 3x squared plus x. So we've defined the symbolic variable x, and we've defined dy, the function we want to integrate, as 3 times x squared plus 1. Now we can simply call the function int to find the derivative, or actually the integral, or the integration of 3x squared plus 1 with respect to x. So you can simply type int and then provide dy as an input to the function int. If we hit enter, the result will be the indefinite integral of the function that we've provided, which is dy. And if you compare this with the manual solution, you'll notice that they're equivalent. And if you remember, we said that integration is the inverse operation of differentiation. So if we take the derivative of the expression on the right-hand side, it will become 3x squared plus 1, which is what we see inside the integral here. Now, if we want to calculate the same integral, but this time as a definite integral with the limit 0 until 1, we can use the same function int dy, but this time we need to provide it with the limit of the integral xmin and xmax as such. So the result, if we hit enter, will become 2, which is equivalent to evaluating x cubed plus x at 1, and then minus x cubed plus x at x is equal to 0. The result, if you calculate it manually, becomes exactly 2. Since this is analytical integration, it is equivalent to calculating the exact integral. Now moving on to numerical integration. Remember that numerical integration is the approximation of the integral using numerical techniques. In MATLAB, there are different functions that compute the numerical integration, such as the trap-z, or the trapezoidal method, function integral, which uses the global adaptive quadrature. There is also the function quad that calculates the integral, the numerical integral, using the adaptive Simpson quadrature method. And finally, quad-l, which applies the adaptive Lovato quadrature method. But we'll mainly focus on trapezoidal method and the integral function that uses the global adaptive quadrature. But notice that the remaining two methods can be used exactly the same way as you can use the integral method. Now we're going to do an example on the function trap-z to help you better understand it. This function depends on the trapezoidal method, which depends on the concept that says the integral is similar to calculating the area under the curve. So with the trapezoidal method, you're going to divide the curve or the area under the curve into smaller sections of the shape of the trapezoidal shape, such that you calculate the area of each and then add them together. So the smaller the trapezoid, the more accurate results you're going to obtain. You use the trapezoidal method when you have a set of defined data points as opposed to the expression itself. So for example, here we have x is equal to 0, increment by 0.01 until it reaches 1, and y is defined as a function of x, but at the end of line 2, the second line of code, we only know that x and y are numerical arrays rather than the expression itself. So we're going to deal with x and y as a set of data points rather than an explicit function definition. Now, if we want to calculate the integral of y, the definite integral of y, with the limit 0 until 1, we can simply call the function trapz and provide it with x as the first input and then y. So if you translate this to English, it becomes calculate the integral of y with respect to x. So remember, for the trapz method, you put the independent variable first and then the function. So trapz x comma y means calculate the definite integral of y with respect to x. And since it's definite integral, that means there is a limit, and the limit is going to be the first element in x as x min, and the last element in x as x max, which is 1 in this case. So this is equivalent to calculating the integral of 3x squared plus 1 with respect to x from x is equal to 0 until x is equal to 1. And the result of this numerical integration is 2, which happen to be exactly matching the exact value that we obtained using the analytical integration. So this approximation happened to have 0 error. Now we'll learn how to use the integral function to compute the numerical integration. In MATLAB, the function integral uses the global adaptive quadrature technique, and it is used when you know the function as an expression. And it is used as such. You first type the function name, integral, and then you need to list the inputs in that particular order. First, you need to provide the function handle, then the limit of the definite integral, x min and x max. The function handle is basically another way to express an expression symbolically in MATLAB. You first use the @ sign and then use a bracket, and in between the brackets you list the independent variables such that after typing at bracket x, what follows is purely an expression of x, or what's in between the brackets. In this case, it's x. So this is equivalent to saying calculate the definite integral of y with respect to x from 0 until 1 using the numerical technique, the global adaptive quadrature. Or if you express it as a mathematical expression, it will be the integration of 3x squared plus 1 with respect to x from 0 until 1. If you hit enter, the result will be 2, which is equivalent to what we obtained earlier. But remember, even though here you're providing the expression itself as an input, the integral function in MATLAB applies numerical techniques to calculate the integral. So it is an approximation at the end of the day, but with a very small error percentage. To know more about the function integral and the error margin, you can use the help command in MATLAB by typing help integral to learn more about it. Now we'll move on to the last topic of this lab, which is solving the ordinary differential equations with the help of MATLAB. MATLAB includes different functions that solve ordinary differential equations of the form y prime is equal to f of t comma y. That means you have to have the functions written in terms of first order differential equations. So that means if you have a system of higher order differential equations, you need to reformulate them and write them as a system of first order expressions. This is all applies to if you want to use the numerical techniques in MATLAB. So some of the numerical methods in MATLAB that helps you calculate or solve an ODE system is the ODE 45, ODE 23, and ODE 113. And these are all different techniques that can be used to calculate the numerical solution. But notice that not every differential equation can be solved using the same technique. That's why you'll have to try different methods until you're able to reach a solution. But all of the methods, ODE 45, ODE 23, and the rest of them, they all use the same format. So it is easier for you to try different techniques. And for that reason, also, we're only going to focus on one of them, which is the ODE 45. So the points I've listed so far all apply to numerical techniques of solving ODEs. But you can also solve an ODE system in MATLAB symbolically with the function dsolve along with the symbolic math toolbox. And you can still solve higher order differential equations or dsolve without having to reformulate the system. The ODE 45 function makes the best choice for a first guess numerical technique to use if you don't know much information about the equations that you want to solve. The function is used as follows. It has two outputs. First is the independent variable, or the x coordinates. Usually it's time. And the second element is the vertical coordinates of the data points, or the dependent variable. And if you do not specify the output of the ODE 45, and instead you just use it as it is without creating a variable for storing the output, then the function will plot the results. So it will plot the solution for you, but without any labels, so you'll have to add a title, labels, and all of that. You'll have to input a function handle as the first input, and it can be in the form @ty if the function you're trying to solve is a function of t, or it's named y of t. And you'll have to use a function handle as such. So function handles are like symbolic math, or like symbols in MATLAB, except you don't need to define any symbols at all. You can just directly use @ and then in between brackets you list the independent variables, and then you type the expression as a function of the independent variables. The second input is the initial and the final values of t. So whatever value you see for t at the output, you can determine the initial and the last entry in t using the second input to the function ODE 45. So it's an array containing two numbers, t0 the initial time and t final, so t1 and t end. But MATLAB will determine how many points it is necessary to use in between, or the length of t. But in the second argument here, you will specify where to start and where to end. The last input for the function ODE 45, or for any numerical solver for ODEs in MATLAB, is the initial conditions array. It could be just one scalar or an array depending on how many ODEs or how many equations you're trying to solve. So the initial condition is basically the value of y at the initial time, so y at t0. Now we're going to see an example of first order differential equation. We're required to solve the following differential equation. So we're given that dy dt is equal to 2t, and we want to solve it for the interval t is equal to 0 and t is equal to 5. And we're given the initial condition y at 0 is equal to 0. So we can first what we need to do first is to define the function handle. So dy dt is a function of t and y. So even though y doesn't appear in the expression, but the expression is actually a function of of y. So dy dt at t comma y, meaning what I'm going to write next is a function of t and y. And the expression is 2 times t. So this is the definition for my function handle. Next, I'm going to define the interval. T0 is equal to 0, t final is equal to 5, and my condition is y0 is equal to 0. Finally, I'm going to apply the function format that I've learned in the previous slide by saying y is equal to, or t comma y is equal to, ODE45, the function handle dy dt, and then the array containing the time interval, the initial and the final time interval, and then finally the condition. So now, after hitting enter, what I'm going to see in T is an array whose first element is T0 and last element is TF. And Y is going to be the array of the solution. So it's a solution for dy dt is equal to t. If instead of assigning t comma y as the output of the function ODE45, you just type ODE45 directly without assigning the result to an output as such, then the result is going to be a plot of the solution as discussed earlier, but the plot you will see will not have any titles or labels. So if you want to add a title and a label, you'll have to explicitly mention it in the code. So here I added x label as t, the y label is y, because the solution is a function of t, so it is y of t. And as a title, I just type the solution of dy dt is equal to 2t, and observe that the function I'm trying to solve here is dy dt is equal to 2t, and the function that I can see in the plot is equivalent to t squared, right? Notice that at 0, y of t is 0. At 2, y of t is 4. At 5, y of t is 25. So this is equivalent to t squared. And if you take the derivative of that, it becomes 2t. So we can now verify the accuracy of the solution. We can tell that it's accurate. And according to the question, we want to solve the system for the interval 0 and 5. So the x-axis should be ranging from 0 until 5. And the initial condition I was provided is that at 0, y is equal to 0, which is true for the case, for this case here, as you can see from the plot. Now we're going to do an example of a higher order ODE system. The question says solve the following ODE. So you're given that the second order derivative plus the first order derivative is equal to the function self y plus t. And we're aiming to solve this system or this differential equation on the interval t is equal to -1 and 1. And we're provided with the initial conditions as follows. So y of -1 is 0, y prime, or the first order derivative, is 0 at -1. The first step we're going to do in the solution is to rewrite the expression as a system of first order expressions for us to be able to use numerical techniques in MATLAB. Because if you remember, we said that the system has to be written as a set of first order differential equations. So what we're going to do is rearrange the equation that is given so that it will be written as a set of first order expressions. So let me rewrite the expression itself as y prime instead of dy dt, y double prime instead of d2y over dt2. So this is just another annotation or another annotation for the expression itself. I didn't change anything else. The first step we're going to do is substitute each time we see y with y1. This way, we'll be able to number our equations of first order expressions or first order derivatives. So every time I see y, I'm going to replace it with y1. So it will be y1 double prime plus y1 prime is equal to y1 plus t. Next, what I'm going to do is substitute y1 prime with y2. So this will apply to any system that you may have. You'll still do the same things here. So the expression becomes y2 prime plus y2 is equal to y1 plus t. Next, I'm going to find an expression for the first order derivatives, y1 prime and y2 prime. As you can see, y1 prime is already given here. I already defined it myself. So y1 prime is equal to y2, because that's how I defined it earlier. So this is equivalent to this line of the solution. And next, I need to find an expression for y2 prime. This is y2 prime. So I only have to move y2 to the right-hand side of the expression, but with a negative sign. So the solution becomes y2 prime is equal to y1 plus t minus y2. Now I've written the expression as a set of first order derivatives, so it is possible for me to use the MATLAB numerical solver. Continuing with the solution from the previous slide, as discussed, since we splitted the original second-order differential equation into two expressions of first-order equations, now and the function handle now has two rows in it, that means the solution y that we're going to obtain from ODE 45 will have two columns, as mentioned, such that the first column corresponds to the solution y, and the second column, and we can extract the second column using the notation y, y bracket colon, meaning regardless of the row number, I want to find the second column. So the second column, again, in y corresponds to y prime. But we're only interested in the first column in the solution because that is the solution for y itself, which we want to find in the first place. So to plot the solution, we can either plot everything and add a legend to describe them. So we can say plot t comma y, but since y has two columns, the result will be two plots superimposed on top of each other. So there's no need to use the hold on command now because y is already consisting of two columns, and using the function plot t comma y, we'll plot the two columns in y, but it is our responsibility to add a title and legends along with the x label. Here I'm using the double quotation because I need to use the prime or the apostrophe to express y prime. So the first column is y, so that means the first legend should be y, the second legend should be y prime. If instead you just want to plot the first column, or you want to plot only y, then you'll have to say t comma y colon 1. And then you can just simply add a title plot of the solution y, and the x label would be t, the y label would be y. Simply, there is no legend if you only have one plot. Now we're going to move on to how to solve ODEs in MATLAB using analytical techniques. Symbolic solution of ODEs can be obtained using the function dsolve, which has the following form. So the function dsolve takes the equations or symbolic equations as inputs, including the conditions equations. So you'll have to use sims yt to indicate that y is a function of t, and in case you want to express the derivative of y with respect to t, you have to use diff y to obtain the symbolic or the analytical differentiation or derivative of y. We'll see more examples later for you to understand this clearly. And the function y, or the function dsolve, will output y, which is the solution or the symbolic solution of the ODE system. Now we're going to do an example of a first order differential equation using analytical techniques in MATLAB. We'll do the same example we did earlier, but we did it earlier using numerical techniques. This time we're going to do it with the function dsolve so that we can obtain the analytical solution. So we're given that dy dt is equal to 2t, and we're given the condition or the initial condition y at 0 is equal to 0. So it is up to us here to choose the time interval for the solution in case we want to plot the solution later. But by the end of the slide, we'll reach the analytical solution or the symbolic solution for the differential equation that is given. So the first thing we need to do is create a symbol for y of t. So we'll say sims y of t because we want to solve for y as a function of t, and we're given the derivative of y is equal to 2t. Now I can find dy dt by simply calling diff y to get the first order derivative. So what I'm going to do now is write my first equation, which is equation 1 is equal to diff of y, or the derivative of y, is equal to 2t. The second equation I have is actually a condition, and I'll name it condition, or Cont, is equal to y at 0 is equal to 0. So remember, if we're translating equations into MATLAB equations, we'll have to use the double equal sign instead of the single equal sign in the original equation, because the single equal sign in MATLAB means the assignment operator. The double equal in this case means the two sides are equal, so we're not assigning anything here. Next, I'll call the function dsolve, and then I'll assign the result in a variable named y. So y is equal to dsolve, and then I'll list the equations that happen to include the condition equation, of course. So the result was given as y is equal to t squared. To verify the solution, I'm going to take the derivative of the solution. So t squared, if I take the derivative of it with respect to t, is going to become 2t, which matches the equation itself that I'm given. So it is possible for me here to verify the solution, which I did. So I can say or conclude that then y of t is equal to t squared. Now we're going to do a higher order example. I'll do the same example we did earlier with numerical techniques, but this time we're going to solve it using analytical techniques or symbolic solution, to obtain a symbolic solution for the expression. With the analytical technique in MATLAB, there is no need to reformulate the expression. So I can do it as it is without having to reformulate everything in terms of a first order expression. So all you need to do is to create a symbol for our y of t. So I can say sims y of t. And then I will need to define the second order derivative and the first order derivative with the help of the diff function. So sims y of t simply means y is a function of t, and I'm declaring it here. And then dy, short for the dy dt, is equal to the first order derivative, which I can obtain using the diff function. Okay, now I will define the second order derivative, which is part of the equation. So d2y divided by dt squared, or in other words, the second order derivative, I'll use d2y for short, is equal to diff y comma 2. So translating diff y comma 2 in English terms or in mathematical terms, it means the second order derivative. Okay. Now I'll write equations, 3 equations in total. First equation is to represent the ODE. The second 2 equations, or the second equation is for the condition, the last one is for the other condition that I'm given. So I'll say equation 1 is equal to d2y, because it's the second order derivative, plus dy. So I'm just translating the expression into MATLAB code. And then equal, because the 2 sides are equal here, I'm not assigning anything to anything. And then on the right hand side I have y plus t. So I only have one equation and 2 conditions. So the first condition is y at -1 is equal to 0. So I'll name it cont1, or condition 1 is equal to y at -1 is equal to 0. Then the second condition, cont2 is equal to dy at -1 is equal to 0. Now I have everything prepared. I can simply call the function dsolve by saying y is equal to dsolve, and then list all the equations that you've created, including the conditions equations. So equation for the expression itself, condition 1 equation, and the second condition equation. This concludes the solution for the second order equation that is given. The solution was very lengthy, that's why I'm not displaying it here, but instead I'll learn or I'll show you how to plot it. Now, in this slide, we're going to discuss how to plot symbolic expressions in MATLAB in general. So it's not necessarily going to be the solution of an ODE system, but it will apply to any symbolic expression that you have in MATLAB. I'll use the solution from the previous slide as an example. So we have y as a symbolic expression in MATLAB, and you're aiming to plot it. The first method is to use the function EasyPlot. So it's short for EasyPlot, basically. It's just EZ and then plot. And you need to provide the function with the function EasyPlot with these arguments. First, you need to put the symbolic expression, and then you need to provide it with the limit for the independent variable. So EasyPlot y, -1, 1 simply means plot y of t on the interval -1 until 1. EasyPlot can only be used with symbolic expressions in MATLAB. So you only use it for expressions, or you cannot use it for numerical arrays. If you have numerical arrays, you'll have to use the function plot or the bar plot, depending on the application. Without providing the interval for the x-axis, the function EasyPlot will determine the best range that it's possible for it to use. So this is the result that you'll get from EasyPlot. On the x-axis, you'll see t, since y is a function of t, and the function EasyPlot knows that already. And then in the title, you'll see the expression as a function of t. See how long the expression is? It doesn't even fit in the title. For that reason, I didn't want to display it in the previous slide. You can still override the current axis labels along with the title by simply just typing x label, y label, title, and then replacing the current default title from EasyPlot. The second method to plot a symbolic expression in MATLAB is to first evaluate it. So the function subs can be used to evaluate any symbolic expression in MATLAB. So regardless of whether you want to plot it or not, you can use the function subs to evaluate any symbolic expression at certain values for the independent variable. So using the same example from the previous slide, we want to plot the solution for specific values of t. So the first step to do is to define the independent variable, the values for the independent variable. I'll create the array named t, ranging from -1 until 1 with an increment value of 0.1. Since y is the function of t, I had to use the same variable name, the exact same variable name. So I had to use t as it is without changing it. Okay. Second step is to use subs y, and then by default MATLAB will know that it will substitute t in the expression of y with the values that I specified. But instead of doing that in 2 lines of code, I'm going to simply use the plot function as such. So I'll say plot t, subs y. So in the x-axis, I'll see t ranging from -1 until 1. In the y-axis, I'll have the evaluated values of the expression itself at the given t. And then I added a title, x label and y label. So again, you'll use the function subs to evaluate a symbolic expression at a definite variable, at a definite variable that you define for the independent variable. So you need to specify the values first for the independent variable by overwriting it, and then use the function subs. So the result will be a plot of y of t, with the x-axis being t ranging from -1 until 1, and the y-axis is y evaluated at the given range of t. Now we're going to move on to the last topic of Lab 5, which is Simulink. We're going to mainly focus on how to use Simulink to solve ODEs. Simulink is the MATLAB-based graphical programming environment for modeling, simulating, and analyzing dynamical systems. And this is the icon or the logo for Simulink. You can access Simulink by simply clicking its icon in MATLAB environment. Simulink includes a collection of blocks that can be used in a Simulink model, and to access the collection you need to click the library browser, and then you can either search for an item or look for them in the list. To solve an ODE system using Simulink, you need to first represent the ODE system as a model in Simulink. And you can solve the system by simply simulating its model via using Simulink. Some of the commonly used blocks in an ODE model include the integrator, of course. So if you have dy dt and then integrate that, you'll get y. So this is the simplest ODE. You have the product if you want to multiply two numbers or divide them by simply, you can change the settings of the product into division. You have the clock to represent the time or t. You have the gain if you want to amplify a signal in Simulink, and then you can choose the amplification or the gain value. You have a constant, the summation. The sum icon here by default has only two inputs that you want to add together and then one output, but you can adjust the settings of any block in Simulink by double clicking it and checking the settings options and then modifying them. For example, for the sum, you can add more inputs to it and then replace the summation signs with subtraction. You also have the scope, which helps you visualize or plot the result with respect to time. The XY graph also is another way to visualize or plot the results, but instead of having the x-axis being the time, you can specify the x-axis using one of the signals that you have in your Simulink model. You also have the math function, which can be modified in the settings to compute, for example, the square root of a signal or the signal raised to a certain power and so on. There are other blocks that helps you transfer data to and from Simulink. We'll mainly focus on the to file, and then by default the file name is untitled.mat, so the extension is mat, and then you can change that to, for example, data.mat from the settings of the to file block. The block to workspace will help you transfer data to the workspace in MATLAB, so you can process them later on in MATLAB. So, for example, instead of using the scope, you can transfer the data to a file, a .mat file, save it, and then process it later in MATLAB, whether you want to plot the data or just look at them or tabulate them, for example. Here's an example of a first-order differential equation. dy dt is equal to 2t, which is the same example we did earlier, except here it's simulated as a Simulink model. So we have t as a variable, so that's why we placed the clock as a block. And then we have 2t, so we need to multiply t by 2. That's why we placed the gain component. And then that concludes the expression itself, 2t. So 2t is dy dt. We can simply integrate it to obtain the original signal, which is y. So y, the signal y, is the final solution, but we add a scope block for us to visualize the result by double-clicking the scope block and then running the simulation. I've also added a two-file block, and I named the file as data.mat. This way, when I run the simulation, I'll have the result of y stored in a file, so I can plot them later on in MATLAB. You can choose the end time from the simulation bar. It is very easy and user-friendly to use, so we'll have a separate video explaining how to open Simulink and then simulate an ODE system to obtain the solution. So the integrator takes y prime, for example, as an input, and at its output you're going to see y, so the integration of y prime. So if you have a system of second order differentiation, then you need to use two integrals or two integrators blocks. We've mentioned about the conditions or the initial conditions. So for this given problem, the initial condition is y0 is equal to 0. By default, the integrator will have the initial condition set to 0, but if you want to alter that, you can simply double-click the integrator block and then adjust the settings of the initial condition from there. And finally, like I mentioned, to transfer the result of any signal into a script file, you need to first store it in a data file or in a .mat file by placing a two-file block and then running the simulation. To read the data within a script file, you can simply use the command load, and then in a quotation mark you put, or in between quotation marks, you need to place the .mat file name. So the command ysim is equal to load data.mat simply will read the value of y that is stored in the data.mat and store them in ysim. So the variable name is ysim. You can change it to anything else, but I used ysim short for y from Simulink. Here's another example of solving ODE systems. It is the second example we did using numerical techniques along with symbolic math with the function dsolve. So we have d2 y dt2 is equal to y minus dy dt plus t. And you're given the initial conditions so that y at -1 is 0, y prime at -1 is 0. Since the initial conditions I'm given, or the initial time is -1, that's why I placed a delay component so that I add a delay of 1 time unit. This way my time will start at -1 instead of the default starting value, which is 0. And then again, you can set the initial conditions by double-clicking the integrator blocks. And to make things easier, I've labeled each of the signals that I have in my Simulink model, such that this signal, for example, here is y double prime This is y prime, and the output of my final integrator is y, which is the solution. And I finally placed a scope to visualize the result or to plot them as a function of time. I also needed to adjust the settings of the scope such that the x-axis ranges from -1 until 1 instead of the default 0. So instead of starting at the default value equals to 0. Thank you for watching, and if you have any questions related to the lab topics, please use the discussion forum on Moodle.